So here we have the function age a of x that's equal to the exponential minus a modulus of x, and a belongs to the real numbers and a is greater than 0. Okay, so the question 1 is asking us to show that age of a of x belongs to L1, and also we need to calculate the Fourier transform of the function. So for question 1, first we need to prove that the function belongs to L1. So we're going to approach this by the definition. So we're going to integrate our function, the modulus of our function, actually. And we need to find anything that's less than plus infinite. All right, so here we can remove the modulus since the exponential is always positive, so it's the same thing. So we can write simply the integral of our function. So now we gotta separate our integral considering the two intervals, so minus infinite to 0 and 0 to plus infinite. By doing this, we are separating the values of x that are negative and that are positive. And when we do this, we can analyze properly the question of the modulus here, so we can remove it. So when we're integrating, considering negative values for x, the function modulus of x is actually minus x. So the minus will cut out with this minus a, and we're going to integrate actually a exponential of ax dx. And if we're considering positive values for x, the function modulus of x is equal to x. So here we are going to integrate minus ax here as the power of the exponential. So just calculating the primitive here, we'll have exponential of ax divided by a. This goes from minus infinite to 0. And here we have the other primitive that is exponential of minus ax divided by minus a. And that's going from 0 to plus infinite. All right. So substituting the values here, we'll have a to the power of 0 divided by a, that's 1 divided by a. So 1 divided by a. And now we have minus, and now we are going to substitute minus infinite. If we have an exponential of something that goes to minus infinite, we are going to decrease to 0. So that's basically minus 0. So I'm just not going to write it here. Now we're going to analyze this one. So here we have when we're going to substitute plus infinite, we're going to have an exponential of minus infinite. So that's the same case, we are decreasing to 0. So that's plus 0, so I'm not going to write it. And now we have minus, and we are substituting 0. So when we're going to substitute 0, we are going to have this minus a here. This minus will cut out with this minus here, so we'll have plus. And when we substitute 0, we'll have exponential of 0, that's 1. So we'll have 1 divided by a once again. That's 2 divided by a. And since our a is a real number greater than 0, it means that we won't have 0 in our denominator, so it won't diverge. So this is surely less than plus infinite. So since the integration, considering the real numbers of the modulus of our function is less than plus infinite, by definition, this function belongs to L1. Okay, so that's half of the first question. So in the other half, we need to calculate the Fourier transform of our function. Okay, so since our function belongs to L1, it means that we can calculate the Fourier transform. So for any value of x, now we can write down that our function transformed, so aj hat of x. Here we're gonna write our function in t because we want our Fourier transform to be in x. So the domain of our function, of our original function, must be in t. We have the freedom to choose that. So here we're gonna integrate ha of t times the negative exponential of 2 pi I xt dt. That's basically writing, once again, dividing the intervals in positive and negative because of the same thing. We're gonna have minus infinite to 0 here, and that's negative values for x. That means we will have um, exponential of, here it will be a minus 2 pi I x t dt. And if we have positive values, we'll have exponential of minus a minus 2 pi I x t dt. All right, here we just did the same thing. When we separate integrals, we are only considering positive or negative values for x, and with that we can open the function modulus of x on the power of the exponential, and we can write it properly like that. So now we can integrate and calculate the primitives. We'll continue here. Let's put it down here. So the primitive of this one would be the same exponential divided by the coefficient of the exponent of the power. So a minus 2 pi I x. This is going from minus infinite to 0. And in the other one, we'll have the same exponential. So minus a minus 2 pi I x times t divided by the coefficient. And this is going from 0 to plus infinite. Okay. So here we have something particular. So let's analyze only this first. This is the same as exponential of a t times exponential of minus 2 pi x t I. Okay, I've just written it on a product, but it's the same thing. Okay, we just sum the powers when the base is the same. So I've just written the numerator on a different way. Okay, when we substitute plus infinite or minus infinite, it doesn't matter. Here is the real part, so it's like no imaginary numbers, so there's no I here. So when we substitute, for example, in this case, we'll have minus infinite here. So we'll substitute minus infinite, we'll have 0, because it is an exponential of something decreasing infinitely, so it will be decreasing to 0. So this will be 0, okay? And when we put minus infinite in here, a lot of people just get confused because here there's a minus and here there's a minus, so it will be positive, and you will substitute this infinite here on the t, so it will be an exponential with a power, with a positive power that is going to infinite. So it seems like this is plus infinite, but in fact it isn't because of this I here. It says that this exponential is not real, so it is imaginary. So in fact, we need to remember that the exponential of I times theta is equal to cosine of theta plus I sine of theta. In fact, it means that when we have our graph here of the imaginary numbers as the y-axis and the real number as the x-axis, we have basically a circle. Here is our angle theta. So this is the imaginary part that is relative to the sine. And here we have our real part that is relative to the cosine theta here alone. And here is our exponential of I8 theta. And the norm, so the value of this is always 1, since it is basically the radius of our circle. So it doesn't matter how much you increase your theta, because that's what we are doing when we are putting infinite here on the t. We are just increasing the value of theta. When we are doing this, we are not changing the value of the module of it. We are just basically rotating our uh, our exponential of I theta by changing the the value of theta, but we are not changing the module itself. The module is always 1. Okay, so that's basically the Euler formula that says that the module of exponential of I theta equals 1. That's basically it. I guess you've probably seen this. All right, so here we won't really analyze the infinite when it's when it comes along with the I here. It's always 1. Okay, it only matters the real part. All right, so I'll do it quickly right now since I've done the explanation. So here when we substitute 0, it will be exponential of 0, that's 1. We're going to divide it by a minus 2 pi ix. When we substitute here minus infinite, we'll have a negative exponential of a negative power, so it's decreasing to 0 since it's going to infinite. And the imaginary part, it doesn't matter. So the imaginary part, it doesn't matter. It's going to it's always 1, so it doesn't matter. Okay. So now analyzing the other one, here when we substitute plus infinite, we're going to have the same thing. The real part is decreasing to 0, and the imaginary part is always 1, so we'll have 0 times 1, that's 0, so it won't add any value for us. And when we substitute 0 here, we'll have exponential of 0, that's 1. So we'll have minus 1 divided by minus a minus 2 pi ix. We can cut this minus here with those minuses here. So I will just write it as a plus here and a plus here. Okay, so basically we'll have this. And now in order to solve this, we're gonna just multiply the denominators. Here we'll have a plus 2 pi ix plus a minus 2 pi ix. So that's basic math. Here the minus 2 pi ix will cut out with this plus 2 pi ix. So we'll have 2a in the numerator. And here we'll have a squared plus 4 pi squared x squared. So that's our final answer. So the transformation of Fourier of our function aj of x equals 2a divided by a squared plus 4 pi squared x squared. All right, so I guess the first question we've solved. So we've shown that that our function belongs to a 1. we calculated the Fourier transform. And now in question 2, we need to show by definition that HA of x double hat. So you've transformed, you've Fourier transformed 2 times our function equals actually the function. Okay, so in order to do that, we're gonna write down here. So question 2. Okay, so HA of x with a double hat, that means that we are gonna use Fourier transform on the function HA hat of x. Okay, so we are gonna transform this function. All right, how we do that? We do that by definition, so we're gonna use the formula of the integral. So here is the function that we are transforming, and which function we are transforming. We're transforming this function, right? Times the exponential of minus 2 pi I xt dt. So by definition, that's what we're doing. That's the transformation of Fourier of the function HA hat. And that's the same as writing the integral of HA of hat t times the positive exponential here, the power is positive, 2 pi I minus x t dt. Okay, so I've just dislocated the minus sign here. I put it along with the x here, so it's minus x, okay? So if we consider it like this, so the power here is positive, that's the formula of the inversion of Fourier transform, okay? So this is the inversion. So if we are inverting Fourier transform, it means that we are inverting this function right here. So if we're inverting HA hat, we're gonna have HA. Okay, so this is equal to HA, but calculated in minus x, since that's our new variable here, since we've dislocated the minus, okay? All right, but our function HA is a pair function. So by definition, this is the same as writing HA of x, because the function is pair. If it isn't clear, I'll just quickly explain it. Our function HA of x is equal to exponential of minus a modulus of x. So here, because of the fact that the modulus function is a pair function, our function is as well a pair function. So let's suppose we have x equals 2. That means that this will be like exponential of minus a modulus of 2. That's basically exponential of minus 2a. And now let's suppose that we'll have x as minus 2. So we'll have exponential of minus a modulus of minus 2. Modulus of minus 2, that's 2. So we'll have minus 2a again. So you can see that if you choose x or if you choose minus x, you'll have the same value of the function. That's the definition of a pair function. All right. So just to clear it out, what I've done here, we've started from the HA double hat. HA double hat, that means we are transforming HA hat. So that's what I've written here. So here I've dislocated the minus sign. So I've inserted it here along with the x. And now since we have a plus here, so a positive power, that's the inversion. But since we have a minus x, we are not inverting it to the original variable x. We are inverting to minus x, but that's the same as h of x since the function is paired. So that's the process of thinking. All right, so question 2 is solved. And now in question 3, we need to calculate the Fourier transform of a squared divided by a squared plus 4 pi squared x squared in function of a. All right, so here we're going to use, as usual, something that we've calculated on the previous items, so in the previous questions. So he wants the Fourier transform of a squared divided by a squared plus 4 pi squared x squared. So here we're going to use something that we found on the first question, okay? Because we know the transform of Fourier of 2a divided by a squared plus 4 pi squared x squared. This is something we know. So I'll write it down, and now I will make this equality a real equality, because right now it isn't the same, so I can make an equation out of this. So here we have a squared, and here we have a. So I'll multiply it by a. And here we have an extra 2, so I will divide it by 2 here. So now we have an equation. This is equal to this, right? So what he's asking for is the same as this, all right? So that's a divided by 2, and this transform of Fourier is actually the transform of Fourier of h a of t, right? We've done this. Okay, so now we'll have a double hat. So a double hat. And we've proved in the previous question that this is equal to a divided by 2 and just the value of the function on the variable x, okay? And that's simply a divided by 2 times exponential of minus a modulus of x. All right, so we've solved based on the results that we found on the previous question. So this will happen all the time. And now talking specifically with students from Centralille, all questions that are on the poly and all questions that are on the exams, they usually depend on a result that you found on previous questions and previous items. So it's a logical sequence, okay? So if something seems like very difficult to understand or to find the answer, you probably need to look at the previous items, and it will give you a tip. It will give you a hint on what to do. Okay, so right now we've finished question 3, and now question 4 is we need to calculate the derivative of this. All right, so we need to calculate derivative of a divided by a squared plus 4 pi squared x squared divided by dx, okay? So if we have a derivation of a division, so the derivation of f divided by g, that's equal to f derivated times g minus g derivated times f divided by g squared. So that's the formula that we're going to use. So since a is a constant, here we'll have the derivation of a constant times g, that's 0. So here we have minus the derivation of g. So if we derivate here, these 2 will fall, and we'll have 8 pi squared x. So that's the derivation of g, and then we multiply it by f. So here we'll have a squared actually, because let me see the question again. Yeah, here we have, it asks for the derivation of a squared. So I've written here incorrectly. It's a squared. So here, a squared. All right. And we are going to divide this by g squared. So a squared plus 4 pi squared x squared. All this squared. So that's the answer. It's just a simple derivation. You're probably asking why we're doing this, and the answer is what I just said a few minutes ago. We're gonna probably use this result on the next question. So question 5, we need to calculate the Fourier transform of a squared x divided by that thing. All right. Okay, so question 5, we need to calculate the Fourier transform of a squared times x divided by a squared plus 4 pi squared x squared, all this squared. So here we're going to do the same procedure. We're going to write down something that we've calculated on the previous item. So here we're going to put minus 8 pi squared, a squared x, okay, divided by the same thing. So that's the derivation of the function that we've derivated on the question 4. And now we need to divide it by minus 1 and minus 8 pi squared. So now we maintain the equation. So this is in fact equal to this. All right, so this is minus 1 divided by 8 pi squared times the transform of Fourier of, let's say that s of x equals a squared divided by a squared plus 4 pi squared x squared. So then this is s, the derivation of x. Okay, so this is equal to minus 1 divided by 8 pi squared times s derivated hat. And now, since the Fourier transform is stable by derivation, we're going to use the formula that I've written on the theory video. So basically, if you have a function f derivative k times the transform Fourier of it will be 2 pi I x, all that to the power of k times the transform Fourier of the function not derivated. So that's the formula. We can substitute f by x. So now it's literally what we have here, and the derivation is 1, so k equals 1. So we'll have this, so we can rewrite it as minus 1 divided by 8 pi squared times 2 pi I x times the transform of Fourier of s. So we need to find the transform of Fourier of this. We've actually already calculated it on here, item 3. So we have 8 divided by 2 times exponential of minus a modulus of x. So we'll have here a divided by 2 times exponential of minus a modulus of x. So this 2 cuts out with this 2 here, this pi cuts out with this square, and we'll have basically minus aix exponential of minus a modulus of x divided by 8 pi. So that's the final value of the transformation of Fourier of this function here. Right? So here we have the question 6. So it asks us to verify if the equation p of x equals that integral, if it has a solution inside L1. If there is a p of x that belongs to L1 and a solution of that equation. Okay, so here, as I've mentioned on the theory video, you need to be able to identify a convolution product. So here it's clearly a case that we have an equation of p of x equals f of x g of x. So here we have a convolution product between f and g. All right, so I'll write it down here. So question 6, if we have f and g here as a convolution product, so let's state f equals 1 divided by, let's see the integral here, 1, 1, and 4 pi squared x minus t squared. So this means that our f here is 1 plus 4 pi squared x squared, and our g is x divided by 1 plus x squared squared. I guess that's it. Let me see. Yes. So by definition, if you have a convolution product here, that's equal to the integration considering the real numbers. So that's the same as the question writes, since we have there minus infinite plus infinite, that's the same. And we have the first function calculated in x minus t times g of t dt. So that's exactly what we have in the question, and that's exactly the definition of a product of a convolution product. So we are basically doing a convolution product using those functions that I've written there, and basically that's equal to p of x. Okay, so that's the understanding of the equation of the question, and well, now we can work with that. The question basically wants to know if this equation it has a solution, so it has a function p of x that is inside L1. All right, so if you have a convolution product uh, equals to another function, in this case p of x will be inside L1 if f is inside L1 and g is inside L1. Okay, so we'll have that basically the norm of p of x is less or equal to f times g. All right, so in order to prove that our p is inside L1, we need to calculate the norm of f, the norm of g, and see if basically if f is in L1 and g is in L1. We can do that by different ways. You can do this like precisely by integrating f on the real numbers. So you're gonna do this integration here, like the modulus of it, but here we have x squared, so it's the same. Uh, you are gonna do this using the primitive that will be arctan, so trigonometric integration. This will give you, I guess, 1 divided by 2, something like that. You can do it by using this. And this integration here you can do as well as doing modulus of x divided by 1 plus x squared squared dx, real numbers, real numbers. So you can do this one by using substitution. So if you do 1 plus x squared equals u, you can solve this one as well. So you will find a value here, you will find a value here, and you will see that this is less than plus infinite. You see that this is less than plus infinite. So it means that g is inside L1, and it means that f is inside L1. So by definition, p of x is inside L1. So that's a way of solving it. It takes a little bit of effort because you'll need to do those two integrations here. So what I'm gonna do, it's way simpler, I guess. but it demands uh, a little bit of experience on identifying which function you're going to use to compare. But here we can compare first the function f, the modulus of x. This is less or equal to 1 divided by 1 plus x squared. And also the modulus of g is less or equal to 1 divided by 1 plus x squared. So those two states are, are true. And well, if you integrate the real numbers the modulus of 1 divided by 1 plus x squared, you can remove the modulus since the function is always positive. This is equals to pi. Uh, the primitive is arctan. You can substitute using limits, minus infinite, plus infinite. But actually, this is a very common function, so you should know maybe by heart that the value of this is pi. So it's very, very easy to see this. And well, so then it's less than plus infinite. It means that this function that is very common to use as a comparison function to prove that any other function is inside L1. Well, this function belongs to L1. Okay, so since this function belongs to L1 and it is greater or equal for all values of x compared to f and compared to g, it obviously means that f is inside L1 and g is inside L1 as well. Okay, so that's basically the idea. You can calculate the functions or you can use comparison with another function. That's a very useful function to know by heart the value of the integral here, that is pi, and you can prove it by this method as well. So yeah, basically that's the idea. Just summing it up, we've realized that the equation that the question gave us is actually a convolution product between f and g, and we know by definition that in order to p belong to L1, if we have a convolution product, then f needs to be inside L1 and g needs to be inside L1. That's sufficient to say that p of x is inside L1. So we've proved that using comparison with a function that we know that is inside L1 and is greater or equal all the time compared to the modulus of f and to the modulus of g. Or you can calculate f and g, the integral, and well, you reach the real numbers, so it does not diverge. So f belongs to L1, g belongs to L1. That's sufficient to say that p of x belongs to L1. Okay, so question 6 is solved. And now we need to analyze the Riemann-Lebesgue theorem. So let's do it. So question 7 here. Let me see. We need to verify the statement of Riemann-Lebesgue. So basically, let me define again the statement. So the transformation of Fourier of your function, if it goes to plus infinite, so it diverges while x goes to plus infinite, that means that the function not transformed does not belong to L1. That's what the statement says. So we already calculated on the question 6 that p of x belongs to L1. So we've calculated this. So when the question asks us to analyze this, what we want to find is that when our x goes to infinite, we can't we can't find out that our transformed Fourier of our function p diverges. Because if it diverges by the statement of Riemann-Lebesgue, then the p of x can belong to L1. But we found out on the previous question that it does belong to L1. So that's what basically can't happen. Okay, we need to calculate the p hat. We need to make our x goes to plus infinite. And we need to find out that the transformed Fourier of our function p does not go to infinite. That's what we want to analyze here, okay? So that's the statement, and now let's do the work. So we have that f, the convolution product between f and g, that's equal to p. So since the Fourier transformation, it has the injectivity property. We can apply Fourier transform on both sides of the equation. So here we'll have f times g, both transformed, equals p transformed. So if we want a transformed function in x, we need to write down here that our original functions, they are in t. That's just a question of choice, not obligatory, not mandatory. All right, so here we first need to calculate the transform of Fourier of f. So let's do it. That's the transformation of Fourier. F is 1 divided by 1 plus 4 pi squared t squared. Okay, that's this transformation. We already have the value because we've calculated on question 3. The transform of Fourier of a squared divided by a squared plus 4 pi squared x squared. So if we pick a equals 1, we'll have 1 here, we'll have 1 here, and we'll have basically f. So yeah, and the Fourier transform will be a divided by 2, so 1 divided by 2, exponential of minus a modulus of x, so 1 modulus of x. All right, so here we'll have 1 divided by 2 times exponential of minus 1 modulus of x. So that's the answer. Now we need to calculate the Fourier transform of g. That's a little bit more complicated. So once again, our g is t divided by 1 plus t squared squared. Well, let me do this, and afterwards I will explain. So you can see that this equation is valid since we can cut out this 4 pi squared. Oh, sorry. Can cut out with this 4 pi squared with those. So it will be 1 plus t squared squared. So it will be the same thing. All right, so that's a valid equation. I've just rearranged them. And now it's easier to visualize that we already have this value of Fourier transform, because if we go to our question 5 and we substitute, let me erase this, a equals 2 pi, we'll have here 2 pi squared, so 4 pi squared x divided by 4 pi squared plus 4 pi squared x squared, 4 pi squared plus 4 pi squared x squared. So I've just substituted this value in here. And now we can cut out this 4 pi squared with those. So I'll just erase this, and here it will be 1 plus x squared. All right, so if we substitute a equals 2 pi, we'll have this, and this is exactly what we have here. All right, so we can just use the result that we found to the transform of Fourier here. The value is this, so we'll just substitute 2 pi in this a. So let's do the calculations here. It will be minus 2 pi I x exponential of minus 2 pi modulus of x divided by 8 pi. So this 2 cuts out with this 8, so we'll have a 4 here. And this pi cuts out with this pi. So we'll have basically minus ix exponential divided by 4. So that's 4 pi squared times minus ix minus ix, I forgot, minus ix, yeah, exponential of minus 2 pi modulus of x divided by 4. That's it. All right. So now we're going to cut out this 4 with this 4 here, and we'll reach minus I pi squared x exponential of minus 2 pi modulus of x. So that's the final answer for G, and that's the final answer for F. All right, so now we can rewrite our p hat. So our p hat equals, let's pick the constants here, so in half. So it will be 1 divided by 2 times minus 1 actually. Let's use this minus here. I pi squared x, and the exponential, we have a product, so let's sum the powers. So we'll have minus 2 pi plus 1 times modulus of x. So that's our final answer. And let's analyze this. So the transformed p when x goes to plus infinite goes to 0, because here we have a negative power. This is positive, all right? And when we substitute plus infinite here, we're gonna have a infinite decreasing. It will go to 0, okay? Because the exponential decreasing is way faster, is way stronger than the polynomial increasing, okay? So if we calculate the limit while x goes to plus infinite, will reach 0. And that's fine. That's the analysis of the statement of Human-Lebesgue. If this happens, it only means that this statement here isn't true. Okay, we can imply by this that p of x belongs to L1. We can't say that. We can only say that this, that I've done a rectangle, that's not right, and that's coherent with what we found on question 6. Okay. All right, so the last question here, 7 is done. So the last question wants us to calculate p of x, considering the formula of inversion that the question is giving us. So that's easy. We don't need to think much. He basically gave us the formula, and he wants us to invert the p hat in order to find p. That's easy, okay? Not much to think about. So, okay, let me rewrite. Let me erase this. I'm gonna rewrite our p hat because we're gonna use it. So minus I pi squared x exponential of minus 2 pi plus 1 modulus of x divided by 2. Okay, so if we analyze the formula that he gave us, he said that the inversion of I times t times at. Okay, so let's identify that. Okay. So if we want to find, we're inverting the variables all the time, but basically I want our results to be in x, so what we're gonna transform or what we're gonna invert needs to be in t. Okay, that's why I'm changing the variable. So let's suppose that hat is in t, so I'm gonna substitute here by t, same thing. And now we are gonna have the original function p in x. That's basically why I've done that. All right, so let's identify those three terms. Our I is here, our t is here, and here we have our at. Okay, and minus pi squared divided by 2 is just a constant. So if we do the inverse transformation of this, let me take it out the constant, so minus pi squared divided by 2. Inverse transformation of I times t times exponential of minus 2 pi plus 1 modulus of t. Okay, that's basically our p of x, since we're gonna invert the p hat. And well, the I, the t, and the ATs, they are identified. So now we can use the formula that the question gave us. So minus pi squared divided by 2, it remains since it is a constant. And now we need to multiply it by 1 divided by 2 pi. The question gave that. And then we need to derivate in x the inverse transformation of AT. Well, AT is this, okay? And if you look it carefully, you will realize that's basically an exponential of minus a modulus of t. That's basically the function ha of x that were given on that was given on the exercise. All right, and we already calculated the the Fourier transformation. All right, so this will be I'll write this as being 2a, but the a now is 2 pi plus 1 divided by a squared, so 2 pi plus 1 squared plus 4 pi squared x squared. Okay, this term is this, so I'll just erase this and put this there. All right, so now we need to derivate this. So we've already done derivation of a division, a quotient. So derivation of what's of the f here and the g here. So derivation of f times g, that's the derivation of a constant, times g, so that's 0, minus, so minus the derivation of what's beneath. So these two fall, we'll have 8 pi squared x times what's up, so 2 times 2 pi plus 1 times what's above. And then we're going to divide this by whatever is the function on the denominator squared. So 2 pi plus 1 squared plus 4 pi squared x squared, all that squared. So that's basically the final answer, but let's clear it out a little bit. So this minus here with this minus here, I'm just gonna erase it. Okay, it becomes a positive. This pi here cuts out with this pi squared, so this becomes just a pi, and this pi vanishes. So this pi with this pi squared becomes a pi cubed. So I'm gonna raise it and put a cube here. This 2 with this 2, that's a 4. And 8 divided by 4, that's 2. So I'll erase all that, put a 2 here. 2 with 2, that's 4. So I'll erase that as well, put a 4. And I guess that's all we can do to make it better. So I'll just rewrite it once again, and that's our final answer. So p of x equals 4 pi cubed x 2 pi plus 1 divided by 2 pi plus 1 squared plus 4 pi squared x squared, all that squared. So that's our final value for p of x.